Okay. Okay, so it says synthesize the following. So the original compound is actually a skipdiene, but I don't think you guys didn't learn something called the Birch reduction, right?
No, we didn't.
Okay, so I'm gonna just change the final product. Okay, so we're just gonna start with benzene and give me a second. Let me see how much more I can modify this thing. Okay, so this. Okay, I'll give you guys a few minutes to try that. So you got to start with benzene though, right? And you could use whatever reaction you want. Okay. Some of you might have not been finished by now, but that's okay. So let's get started. All right. So if we're starting from, let's move this over a little. Benzene, right? I think automatic giveaway, right, is you're gonna have to use some sort of, well, you guys tell
BR2,
me.
BR2 and FE BR3.
Um, could probably do that sort of functionalization too. The general type of those reactions, right? What are they called?
Electrophilic aromatic substitution.
Exactly, right? So benzene by itself doesn't have any sort of functionalization, right? But we know we can functionalize it with a variety of electrophiles, right? And then kind of second thing you could look at is that there's this carbonyl group or this acyl group, right? It's one of the carboxylic acid derivatives, right? Specifically, this is an amide, right? So we know there's kind of only a few ways we can get an amide, right? And you're probably going to have to start with one of the reactive uh, carboxylic acid derivatives, which means at some point, right, you're going to have to have an intermediate. Oops, let's make this a little bigger. That looks like this, right? Um, so we know we can't go from benzene directly to an amide, right? Because you guys haven't learned any reactions like that. But we know we could create carboxylic acids or benzoic acids out of benzene, right? I think Ali was saying with bromination, you could type out your root, just send me that privately, and then I'll look over that later. But I'll show you kind of how I did it, which is kind of uses the EAS reactions, and it also uses like reactions of the benzylic position, right? Um, so essentially what we first want to do, right, is add a carbon here, right? Because once we get a carbon here, then we're kind of open to a lot of functionalization, right? And since we're only adding one carbon, right, we could just do a simple alkylation, right? So you could just start with, I don't know, MECl or MEBr, whatever, whichever one you want to use, right? Um, stick to white. Br, and let's say we used AlBr3 or FbBr3, whichever Lewis acid is fine, right? They're both kind of interchangeable. So that first thing that's going to do is that's going to methylate it, right? So once we got this, right, now we have to go to a carboxylic acid, right? Now, did we learn any reactions that could create carboxylic acids at benzylic carbons? It's probably from, I don't know if it's in chapter 18. I'm pretty sure, I think it's in chapter 17. You guys learned this. There's a couple of different ways we could actually go directly from here to directly this carboxylic acid. Good. So Isabel, I'll put one, right? So that's permanganate oxidation, right? So if you use potassium permanganate, right, followed by acid workup or really any water workup, right? You're going to turn into a carboxylic acid. And that reaction, right? So there's actually two reagents you could use. The other one is chromic acid, right? They're just very powerful oxidizers, right? So really, it doesn't matter. So this is just to recall from chapter 17, right? This is a reaction. It doesn't actually matter how big this R group is. It could be like 7 carbons, 6 carbons, right? The whole way this works is that it needs to have some sort of H's at that benzylic position, right? And then you put it through strong oxidative conditions, right? And even if this was 6 carbons or 4 or 5, whatever, it always gets oxidized down to carboxylic acid, right? So, I mean, if you really wanted to, you could have started with the ethyl too, right? The alkyl group wouldn't really matter as long as you create something with those, something that's not tertiary, right? Then it wouldn't work, right? So let's put down what Isabella said. So put KMNO4, and we have here. One second, it's just H plus workup, right? And then the other way would be something like HCr04. I think the book represents this as Na2Cr2O7, sulfuric acid and water, right? That's just kind of a in situ preparation, but the main reagent that's working here is the chromic acid, right? Either one is fine, right? If you put this or if you put that, right? Purpose of this step is just accessing your carboxylic acid, right? Now we have our carboxylic acid. There's not actually too many steps left, right? Can we go directly from a carboxylic acid to an amide? No, right? What's the reason for that?
They will just deprotonate, so we have to convert it to acyl chloride.
Exactly, right? So there's two reasons. I think that was Ali was speaking, right? One thing is if you put it in a solution with base, right, which is your amines, right, just all that's going to happen is an acid-base reaction. Another reason is just it's not reactive enough, right? So we have to turn it into one of its more electrophilic derivatives. So you could turn it into an anhydride, or you could turn it to acyl chloride, right? But acyl chloride is generally the easiest one. So how do we go from carboxylic acid to acyl chloride here? Right, thionyl chloride, right? Pretty simple, right? And then from the acyl chloride to the amide, what's the structure of our amine going to be? Right, so there you go, right? And kind of erase this on the side here, but that is our full synthesis, right? So let me actually look what picture sent me, right? Oh yeah, that works too, right? Perfectly viable way of doing it. So what who was this? Ali sent me is another alternative route, right? And the main thing is like, like that's the whole point of synthesis, right? You have many alternative ways of doing it, right? Generally, as long as you keep it within the same number of steps as his, solution or whatever, right? If you're not doing like, let's say it was a 5-step reaction, if you do it in less step, great. If you do it in like, maybe 7 steps max or whatever, that'd still be fine. But like when you start getting to like 10 steps to do the same thing, you're probably gonna lose points for that. But this one, Ali sent looks fine. So let's show that too. So what he did, right? The main thing is, like I said, with synthesis, it's all about understanding the functionalization you're creating, right? That's really the key to it, right? You just want to access certain groups so you could transform them into other groups. And that's kind of the beauty of organic chemistry is people figured out a lot of way to do that, right? So he started off with a bromination, right? FeBr3. Then he turned that into your Grignard. Oh, whoops, I forgot the BR there. So now you have a aryl Grignard. Doesn't matter though, because the whole point of this, right, is it's that carboxylic acid formation through alkyl halides, right? Basically, what you do is you turn an alkyl halide into a Grignard. You react that with carbon dioxide or dry ice, right? And then essentially what happens is you're adding that carbon in because you have a powerful nucleophile there, right? And this is basically dry ice here is the first step, or CO2, right? It doesn't really matter. they're the same thing. And acid work up H plus H3O plus, right? So now you have your carboxylic acid, and then the final two steps are the same thing, right? So then let's say we go here, right? SOCl2, right? The main thing was understand. That's why I was saying in synthesis, usually there's a few key intermediates you're looking for. And then in my opinion, in this one, right, the key one is if you can get that benzoic acid, right? Because once you access that, as long as it's a viable pathway that you did that through, then the other two steps will, I think, always remain the same, right? I mean, technically you could like, instead of SOCl2, you could use the anhydride, right? But um, like I said, it's all about figuring out that key intermediate. So that's why I always work with the combination of retrosynthesis and forward synthesis, right? You just gotta kind of play around with it. Okay, so let me post the second question for y'all. Okay, so cyclopropene, cycloheptatriene are easily oxidized to their corresponding cations. Cyclopentadiene cannot be oxidized to its corresponding cation. Provide an explanation for these observations. So take a few minutes to try that. Okay, let's go over it. So obviously, as you can kind of see from the structures, right, this is going to be a question dealing with aromaticity, right? So um, really all you have to do is kind of prove whether it's going from a state of, you know, high energy to low energy or vice versa, right? And generally when, things aren't observed, there's a energy pathway, right? So let's look at all the original structures, right? Um, so let's uh, call this A. Oh, whoops, different color here. So A, right? Is it aromatic, non, anti? Non, right? And I think hopefully everyone understands the trend here, right? Is they're all non-aromatic. Reason being, well, let me ask you guys, what's the reason why they're all non-aromatic? Exactly, right? You have an sp3 carbon, therefore there's a position in that ring that is outside of the plane, so it's not going to be planar, therefore it cannot have aromatic stabilization. Luckily, you remove a, what's it called? I guess proton, right? Uh, Actually, it wouldn't be a proton. It would just it would be H minus, right? And then you now have a carbocation, right? So in the first one, right, we have a carbocation, right? So this is sp2 here. The ends of each pi bond are sp2. So how many total pi electrons are in the system? 2, right? So 4n plus 2 equals 2, and that is true for n equals 0, right? So this is aromatic, right? Next one, same thing. Now it's a carbocation. Everything is planar. Let's go and check the pi electrons. How many do we have here? How's it 2 pi electrons? There's only 1 pi bond. There's no pi electrons from a carbocation. If it was a carbanion, right, then we'd have, well, we could possibly have 4. Realistically, it'd just be non-aromatic. N is just like any whole number. Yeah, I meant 2 electrons. Yeah, not like, or 1 pair of electrons. Maybe I said wrong. But N is just it's like any whole number, right? So the rule for n plus 2, right? For n equals 0, 1, 2, 3, right? Then it gives you what? 2, 6, 10, 14, right? So any system that fits the first criteria, which is being planar, right, and delocalized ring of p orbitals, right, if it has this number of total pi electrons, right, whether it's 2, 6, 10, 14, that will have aromatic stabilization, right? So if we look at the next one, how many pi electrons we have, not pi bonds? 6, right? So 6 equals 4n plus 2, and that is true for n equals 1, right? Another whole number, right? Fits the first criteria, fits the second criteria. These are both currently aromatic, right? And now the last one, right? Samia said, right? We're going to find out that's anti, right? So it's locked into sp2 hybridization. So that's the one thing when you have carbocations, right? So remember when we had like heteroatoms, right? If something was about to become anti-aromatic, right, it would rehybridize into sp3 and just go non-aromatic. But the issue with carbocations are they're locked into that sp2 hybridization, and they're going to always be trigonal, planar, and flat, right? So we are fitting criteria 1, right? So we have a total of 4 pi electrons from each of the pi bonds there, right? That does not fit 4n plus 2, right? It does fit 4n, right? Which we can kind of consider the formula for like anti-Huckel numbers, right? That's n equals 1, right? So this is anti-aromatic, right? And essentially we are going from, I guess we'll call this A and B and C. So A and B, we are going from non-aromatic to aromatic stabilization. So that's very favored. And that's why those hydrogens there are willing to be, I guess, removed, right? As opposed to cyclopentadienyl, right? Where the H minus. So just remember, we're moving H minus technically in this case, right? So in that case, if you remove H minus, so hydrogen and its two electrons, right? You're going to form something anti-aromatic. So that's not favored. And then your explanation. I mean, honestly, if you show this, then you have to just say, you're going from a state of low energy to high energy, which would not be favored. And that's why it's not observed. If we had this, so this is just kind of a thing to bring up, right? This is why this is oxidized, because we are removing H minus, right? But if we removed H plus, right? So just remember, because the proton here is acidic, right? These other two protons are not acidic actually, right? But in the case of the last one, this is something I wanted to bring up extra, right? If we deprotonated it, then we get something that is what? Aromatic, right? So, this question could have been asked another way where it said, um, the A and B, the protons are not found to be acidic, right? And then C, the proton is found to be very acidic. Please explain the explanation for this observation. Then you would draw all the carbon ions here, right? Instead of these carbocations, right? And then you'd say that, basically the first two, they will become non-aromatic, right? And, you know, if you did technically count those electrons, it'd be anti, right? And then the last one becomes aromatic, right? So the aromatic stabilization is what makes that proton acidic, right? So technically you could have asked this question a couple of ways. Okay, let's see what the next question here was. Did you guys do the HVC reaction?
Oh no, the professor skipped it.
Skip that. Okay, give me 1 second. Let me because I have to just make sure I put the ones that you guys actually know how to do. And what about electrocyclic?
I don't
Skipped.
think so.
Yeah, he only did sigmatron. Okay, so 2 of these questions I won't post because those are both these. Okay, so I guess I'll just write them out. That's fine. And we have more space to do them anyways. These are just from an old practice final from Andia. This is not Bisco's. It's just very similar in structure, and obviously the topics covered are okay. You guys did not do HVZ. Let's keep going down. Oops. Try to make sure I can show all of these. And then the last one. Last one here is Okay, so take a few minutes to do all of those. Okay, start going over them. All right, so the first one, zoom in here. All right, so we have a base, we have a substrate that has an alcohol group and a Cl minus, right? Let's just say you forgot what these reagents, or let's say you don't know what the outcome of this reaction was, right? Like I said, identify the nature of your reagents. This literally always works. You have a base, you have a molecule with an alcohol in it. What is likely going to be the first step here?
You would deprotonate the OH.
Yeah. So we could just represent this as H minus. I'm just showing the mechanism here because it's simple enough. It's not going to take too much time. right? So we're gonna get this. Yl O minus, right? And now we have a nucleophilic position, electrophilic position, right? Intramolecular attack. This kicks off, and bada bing, bada boom, we get ourselves an epoxide, right? So even if you forgot, you can form epoxides with 1,2 substituted, I guess, alkyl chloride, hydroxyl alkyl halides, or whatever. Right? Could always work it out logically, right? And I'm sorry, I kind of messed up on this reaction. I just realized this is supposed to be styrene. My bad. So in case you didn't get that, right? This is actually supposed to be that. That might make this a lot easier, right? You have a alkene here, right? H2 platinum, right? This is just catalytic hydrogenation, right? Simple enough. Your final answer would just be that. Okay, next one is a reaction of a carbonyl, right? We have KCN, HCN.
Sharuk, I have a quick question. With
Mhm.
H2 and platinum, I won't be able to reduce all of them. It's just the one on the top. Like it won't do anything with the aromatic one.
I think if you have enough pressure and heat, you could reduce it down to cyclohexane, right? But if you have a styrene, like in this case, I just messed up the structure, right? But when you have a styrene specifically, right, it's just basically telling you this is selective towards only the alkene, right? Because generally, right, it takes a lot of energy to break aromatic double bonds because, you're going from something very stabilized to something unstabilized. Right? But I think if you have a proper reactor, you could probably reduce a benzene molecule to cyclohexane using hydrogenation, right? It would just take a lot of energy. But when you have any other additional double bonds or alkene groups, right, it's a selective towards those, right?
All right, thank you.
No worries. Next step, right? KCN, HCN, right? This is a carbonyl reaction, right? Well, no, it wouldn't be changing Me to CN, right? What's the outcome of this? What's a kind of molecule called when you have this O to CN, right? And you also have, so you're going to remove the carbonyl group. The carbonyl group turns into what group?
Is it cyanohydride?
That's what it's
What?
called, right? So that's why remembering the name is going to be helpful too, right? Because cyano means you have some sort of nitrile group, right? Cyanide, hydrin, hydroxyl group, right? So basically, this works, right? It's the CN minus will attack, right? And then the HCN will protonate the alcohol. So your outcome here, right, is OHCN, EME, right? So now what if I change this to, let's say the original starting material was ethyl and methyl, right? I put it under the same conditions. What would be the answer? It would be the same, right? So similar, right? What's the difference here? That's why I brought up this example. Zoom out. It's
There's a
chiral, right? As Serena said in the chat there, right? Just be careful of whenever you do reactions with carbonyls or anything that's, sp2 or what we call prochiral, right? If it had 3 distinct groups and you're adding a 4th distinct group, right? You're going to be making a racemic product, right? So in the first case, we had 2 methyl groups, right? So by definition, you can't have a chiral product because when you do any sort of rotation, you're going to get same thing, right? But now when we have ethyl and methyl, or this could be any 2 different R groups. I just made that example up, right? The whole point is now when the cyanide attacks, right? It can attack from the top face. I guess that'd be the re face in this case, and then the top and the bottom face, right? So you have 2, ways of attacking, which would form 2 different enantiomers. So you could just indicate that it's racemic. right? Or if you want, you could draw one of them on a wedge and this write plus En, whatever you're comfortable with. But there's something I wanted to bring up with the reaction here. Okay. Next one, right, is LAH, carboxylic acid, right? What are we gonna form here? Alcohol, right? So LAH is a very powerful reducing agent, right? And basically you could kind of think of LAH, when you're in a solution of LAH, you're gonna be in very basic conditions, right? So this is literally just gonna remove all the oxygen bonds, right? You're gonna have a H minus attack, kick off OH, and then you have another H minus attack, right? That's gonna open up the alcohol again, right? So here we really just have one carbon. So technically, I mean, you could write, this, you could write MEOH, whatever, if you want to draw it out too, right? All fine. But the main thing is understanding that it's just reducing this completely down to a primary alcohol, right? Okay. Next one, right? Yeah, this is kind of written a little weirdly now that I look about it, but think about it. But I guess it would make more sense if you switched one in the original substrate and the thing. But what kind of reaction is this? This is a chapter, I think 21 is the alpha chemistry, alpha carbon chemistry.
Yeah, so there's no alpha carbons in the one that's next to the arrow. So then you would just deprotonate the alpha carbon in the second, the one that's under the arrow.
Yeah, I can go up a bit. So anyone remember what this kind of reaction was called? You could type it in the chat. No. Malonic ester has to have 2 carbonyls, right? What's the difference between aldol and Claisen?
Claisen is with an ester, aldol is a ketone or aldehyde.
Right. Yeah, if you could do me a favor and just type in the chat, I'd appreciate that. Yeah, so this has esters, right? I mean, this is just a unsymmetrical Claisen yeah, it would be a condensation, right? So basically, what you could do here right, is, yeah, that's why this is kind of written a little weirdly. But I mean, if you could kind of understand that, NaOH wouldn't react with any protons here, right? Aldehyde protons are not, they're not going to ever be deprotonated, right? So essentially, you're going to form this, right? That will react with your aldehyde, right? So while it is unsymmetrical because you have 2 different esters, right? You can only have one outcome, right? Because there's only one pair of alpha hydrogens, right? So this goes attacks here, this kicks off. I'm going to show this in one step. Well, technically 2 steps, right? So the white arrows represent the first step, then you form your tetrahedral intermediate, then the carbonyl here will reform, right? And it kicks off this ester group. Since we are in basic conditions, it could leave, and we get a final product. It looks like, oops. Should be it. Okay, and the last one is acyl chloride. What is this reagent called? Cuprate, right? Lithium cuprate, or it's also specifically, it's called a Gilman reagent, right? What's the difference between this and a Grignard? There you go. Mohammed already said it, right? It only adds once, right? It's much more it's less reactive than a Grignard, right? But they're basically both carbon nucleophiles, and the whole thing is identifying the R group in your cuprate, right? Is your ethyl, right? So essentially, we're going to be adding ET minus to this, right? It's got kickoff Cl, but it won't add again, right? Actually, I don't know why there's water technically in the second step, but yeah, I guess work up with their Cl minus maybe, I don't know. So then you have pH, and you should have ET. Simple enough, right? So that's the kind of stuff you'll expect on the final that's different than all your other exams, right? It's going to be a combination, like the synthesis question. Don't worry, we still have more questions. I'm just kind of reviewing what we've done so far. Is, synthesis question will be a combination of stuff from multiple chapters, right? So, you might combine aromatic stuff with, enolate stuff or carboxylic acid stuff or amine stuff, right? The question 3 here, right? That has, product prediction, right? It's just going to be from anything that you learned in the semester, right? Okay. All right. Let's do the mechanism question. I'll give you guys like 5 minutes to try that out. You know what? We'll just give you till 12. I know sometimes it takes people, but this is honestly a pretty easy mechanism. Compared to at least what you all got in it. But exam 3 wasn't too bad. I think because I was working out the exam while you guys were taking it too. Yeah, the mechanisms weren't too bad. I think I gotta look over it. I believe it was the first one was super easy. I would have suggested everyone to do that one. The other one was a little bit tricky, but once you figure it out, it wasn't too bad. Yeah, I think I forgot which of the top one was relatively pretty simple. Second one, probably, yeah, it's like 4 steps or something like that. It was really just, it was like tautomization stuff, basically. All you're doing is kind of change. I think it was with the carboxylic acid or something, right? Pretty sure that's what it was, right? The second one was a little bit trickier, but whatever. I think I didn't really look at grades, but I don't think the average might have been lower for this exam. I don't know. I think only one person got above a 90. But I mean, there'll be a curve, right? Your raw score. That's the one that's on Blackboard. Anyways, yeah, take until 12 o'clock to do this question. Go get some water. Okay, let's go over this. Someone asked to review the products in exam 3. If you have some time, I could do a few of those. But I have to go by one because I have a lot of people coming over tonight to clean up the house and help prepare and stuff. So I'm going to be leaving at 1. Okay, this mechanism's actually kind of simple. It's just hydrolysis, right? All you're really doing, right, is you are, oh, let me change the group. Oh, switched it back to white. There, and now we have this, right? So essentially what we're doing is, I guess since it's symmetrical, it doesn't matter whether you pick the top or bottom carbonyl, right? So we're just cleaving one of the bonds, right? And this is kind of like what is it? Hydrolysis of an ester, right? As Madrona mentioned there, right? Since we are under acidic conditions, one of the key things here is you do not want to form any negative intermediates, right? So when we're under acidic conditions, right? Let's start with this carbonyl down here. Let's go. Let's make this a little better here. Hey, what's gonna be the hell? I just noticed like a slight screen glitch. Now that's gonna bug me out for the rest of the session. Well, what's gonna be your first step when you're under acidic conditions, right? It's protonation of what though? Carbonyl, right? So this is the most basic thing on the molecule here, right? So it doesn't matter whether you pick top or bottom. Either one would be fine. Let's just go with top, right? So we have H plus, red, right? It's gonna protonate. Right? Now we have this. And now since this is protonated, what does that mean? What happens to this carbon now? It's more what? More susceptible to nucleophilic attack or electrophilic, right? So now we have a weak nucleophile, but we have a powerful electrophile, right? Because essentially you could think of this as a resonance structure, right? So now you could have your water come in and attack. Let's go this way, right? That's going to attack there. That's going to kick this up, right? And now let's go downwards. Have we have OH, right? From our original carbonyl, we have OH 2 plus, right? We have a tetrahedral intermediate. Okay, this kind of first step is like a hydrate formation, right? So now the next step is simply just deprotonation, right? Another molecule of water will just come in. And now you get your geminal diol or hydrate, whatever you want to call it. Right, so now we added our other OH, right? And remember, we're trying to get down to our carboxylic acid, right? So now what can we do next? Is if we're essentially trying to cleave this bond between the carbon and the, I guess, the ester, right? Exactly, right? So it's a reformation of carbonyl. In this case, our group that will be kicked, right, is going to be the OH. But there's kind of like a little thing here is what we'd have to, if we just cleaved it normally, right, what's the issue here, right? It's going to form a negative charge. So what should we do first in order to avoid that? Coordinate it, right? So H plus. Oh, I don't know. I already went to the final product. There you go. OH and carbonyl here. Now we could reform our carbonyl, right? So we could kick off this OH, right? And basically you're going to be done. All you have to do next is just one more deprotonation, right? So this is going to reform. This is going to get cleaved. Now you have a carboxylic acid on the other side. Oh, I forgot my double bonds here. And H here. And your final step, right, is going to be just water coming in and deprotonating your carbonyl and reforming your dicarboxylic acid there. Simple enough. You could technically also do this through base hydrolysis, right? That's the kind of nice thing about esters is there's two pathways to hydrolyze them, right? The only difference with base hydrolysis, right, would be that things would be negative, right? You'd have something like OH minus, it's going to come in, attack, right? Then it's going to just create this as O minus, right? Then it could just cleave off this kind of thing directly, right? And then you'd have basically the carboxylic acid and a deprotonated version of this. It'd actually be, I think, probably a simpler mechanism. And then all you need is water to kind of just protonate it. But with mechanisms, usually it's acid catalyzed stuff because it's more about testing electron flow, right? If you understand what arrows do. Okay. So the next one is an NMR question. The NMR spectra that was originally given here is kind of like, I'm pretty sure it was taken from like a real life example. So I'm just going to give you one that I generated for it with ChemDraw. And I'll give you the compound name. You guys work on it. 5. Sorry, not compound name. C7H12O2. That's our thing here. Let's take a picture of this NMR. I'll give you the integrations and stuff. I get the formula right? Yeah, I did. Okay, so integration wise, this is me also in case the multiplicity isn't clear. Right, this is 1, this is a quartet. This one should be 2, also a quartet. Now, technically you have 2 here, so there's this one is 3 and this one is also 3, right? This one is a singlet, this one is a doublet, right? And then the last one you have there, right here is integration of 3. This is a triplet, right? So use your NMR strategies or whatever it is, however you solve them. And the original question gave you IR, but I know I don't think Boson does it anymore either. So either Professor Bisco or Boson do the NMR. Yeah. You should be fine though. I don't think you need the IR stuff. I think you'll be fine. Oh yeah, I meant the IR. Yeah. Obviously you need the NMR spectra. Okay. Let's get started. So this was someone asked for the base hydrolysis, right? It's simple enough, right? It's also called saponification. Right. So really it's just OH minus, it's gonna come in attacked. Only difference is all the intermediates here are negatively charged, right? So you have your tetrahedral, negatively charged intermediate, we form your carbonyl here, right? Then essentially it automatically cleaves, right? The only difference is now you have O minus here. So technically this proton can hop around both of these, right? So that's why you have a second step, which is just acidic workup. And that's why I kind of just mentioned it there. And then that would just protonate it, get your final product. So that would actually be even easier than the acidic version, right? Okay. All right, let's do this. So first thing, any NMR question, right, is you want to do HDI, right, or IHD or DOU, whatever you want to call it, right? So we want to check the degrees of unsaturation, right? So that is 2 times 7 plus 2 plus 12 divided by 2. Oh, wait, no, divided plus 12, minus 12, right? Divided by 2, so 2 times 7, right? It's 14 plus 2 is 16 minus 12 is 4 divided by 2 equals 2. Okay, so we have 2 degrees of unsaturation, right? So you have, so this is where, like I said, just general pattern recognition and stuff will come into play, right? Your molecule is C7H12O2, right? And you know, the IR spectra they included here, right? It gave you, let's take a look at it. There's a sharp peak around the, 1700 range, right? So what functional group does that mean we're gonna have here? At least one of the thing, carbonyl, right? And specifically, right? Well, it's not gonna be a carboxylic acid, right? Because generally for that, see another proton, right? So it's most likely gonna be an ester, right? So we could kind of already deduce that at one portion of this molecule, we're going to have this ester group, right? And that accounts for 1 carbon, 2 oxygens, right? And that only covers, right? And yeah, as Ali said, the carboxylic acid, right? I mean, like I said, if I showed you this IR, there's no broad peak around 3,500, which is the carboxylic acid proton, right? So that would, like I said, you're not going to be given IR, which is why I wanted you to do it without it. But you could figure this out without it because, you have everything you need here. So that accounts for 1 degree of unsaturation, right? But that means we still have another degree of unsaturation, which could be, another double bond or a ring, right? Now, most likely it won't be a ring because that's going to, create a ring. It's going to create all sorts of different peaks here, right? We're going to see a lot of like, what is it? Quintets or whatever, right? So we know it's not going to be rings. So basically we know there's going to be another double bond. And there's also one signal here that kind of confirms you're going to have an alkene, right? Which one is it going to be? If I label these, oops, A, B, C. Which one of these signals is in the alkene range? People forgot it's going to be the first signal, right? A. There's a reason why it's even more downshifted than normal. I think alkenes are between 5 and 7, but that one is very downfield, right? And there's a reason for that. So basically, we know there is an alkene and a carbonyl. Now we can start plotting really the rest of this. Okay, so let's look at signal B, right? We have a quartet, which means that, okay, so first of all, we have an integration of two. That means wherever the carbon signal B is, right, is going to be a carbon, right, with two H's on it, right? And if it's a quartet, how many neighbors does it have? Unequivalent neighbors. 3, right? So it means it's next to another carbon, or maybe even CH, right? Something like that, right? So we can't really figure it out. But the shift kind of, well, man, I gotta stop using white here. The shift here is 4, right? So that kind of actually gives us a big hint in terms of what it might be next to. Well, it will be technically like an ethyl group, right? It is a CH2 group, right? But because it's shifted at 4 plus, it's next to the oxygen. Is it next to the carbonyl directly, or is it next to the ester oxygen? I guess you're technically, you answer the question, right? Because if it's next to the carbonyl, it would be next to carbon. Yeah, so it's next to the ester oxygen, right? So remember when you know, protons directly neighboring a ester, it's like, you know, approximately like 2.5 or plus 3 in terms of shift, right? So normal alkyl protons, right, are around the 1 to 2 range, and now we're shifted almost plus 3, you know. So basically, we could start adding on to the structure, right? Is now we know there is a CH2 group here, right? Now you could figure out another one, right? Is if this is a CH2 group, it has a multiplicity of a quartet, which means 3 equivalent neighbors, right? One side is an oxygen, so there's no neighbors here. What is logically the only group that could be attached here then? CH3, right? Now we know we have one methyl group, right? Let's try to figure out which one of these signals is that methyl group, right? So we have a singlet, a doublet, and a triplet, right? Which one is going to correspond? So a C, D, or E, which one is going to correspond to this methyl group we have here? E, right? Because it's a triplet, right? This methyl group here, right, is only next to 2 unequivalent neighbors, right? So let's start labeling these. E, right? This we said is B and B, and let's just confirm again, right? So B, highly shifted, it's next to the carbonyl or the ester group, right? It is a quartet, so it's next to 3 unequivalent protons, right? HE is a triplet, integration of 3, so we know it's a methyl group, right? 1.2, which is far enough because it's alpha, beta, so it's 2 carbons away. The shift won't really affect it too much. And it's a triplet, which makes sense because we have 2 unequivalent neighbors plus 1 triplet, right? So now we have a portion of the molecule, and we kind of already figured out B and E, right? As well as 2 oxygens, right? Now what's remaining, right, is we have a, what's it called? A carbonyl, right? And we have how many more? So we have 7 hydrogens, right? So we look at signal A here, right? Signal A is in the 6 to 7 range, right? So that is directly connected to our alkene group here, right? So it's vinylic, right? And it's a quartet, which means in terms of an alkene, right? Let's say this is the structure, forget this side, right? Let's say, doesn't even matter what side's here. Let's just look at one vinylic proton, right? So we have only one proton directly attached to alkene. If it's a quartet, that means next to it, right? How many, or I should say on the same carbon, how many, what kind of group is attached there? Quartet means there's 3 unequivalent hydrogens nearby. And remember, for NMR, right, you can go up to the same carbon, right, can couple, or one more carbon, right, can couple, right? So it's a methyl group, right? Because remember, let's maybe draw up these carbons to make this super clear, right? This is a carbon connected here, right? And we have another carbon here, which can still couple with this vanillic one, right? And that's what makes it a quartet. But here, if we have any other R groups, right, whatever, carbons we might have here or carbons here, right? So let's put this in blue. So anything attached here or here can couple, right? Anything technically attached here can couple, right? But these ones circled in red, right? They're too far to couple with this proton, right? So basically, we know that the alkene, right, at this point, right? Where's the white? You have an alkene that has one vanillic proton and one methyl group, right? So now we could cancel out signal A since we already did that. We can now try to figure out which one of these methyl groups, right, is our correspondence. So we have C and D. So C is a singlet and D is a doublet, right? So basically, right, and they're both integration of 3. So now we could kind of tell that the remaining other group is also going to be a methyl group, right? So you could add to, doesn't matter what side of the structure you add it to. Put it here, right? So these are 2 methyl groups, right? Left or right, which one is C and which one is D? So remember, C is a singlet, D is a doublet. That means D is coupling with one unequivalent proton, right? So maybe if I drew this out just to be clear, just so you could remember the coupling, right? Left or right, which is the only one that has forget anything here, right? Because there's not gonna be any proton here, right? Left or right, which is the only one that could have exactly, right? So Isabella there said, right, that has the only thing that's a neighboring carbon, right? Which is the vanillic proton. C, right, because it's a singlet, right? It basically gives us insight that C is attached to the carbon, which is attached to really the rest of this structure, right? And now we could kind of piece it all together. And I think this is probably the hardest part, which I don't think you would lose points on because this is very, very specific, right? So technically it would be this and this. So that's our methyl group, right? We'll write CH3. So I'll call this, what did we call this was doublet was this is D, C, right? So we have another methyl group here. And if this methyl group, right, is a singlet, right? And it's also slightly higher shifted, which means logically it's connected to the carbon that is connected to the ester. Right. And now I think the thing is maybe people are like, how do we know whether it's cis or trans? Right. And this is just kind of one of those trends. Like I said, I think if you drew this or if you drew it like I think you'd probably get maybe like a point or 2 lost at most, but you'd still get majority of the credit, right? Because you figured out most of the structure, right? So the bottom one here, right, is cis. The top one is trans, right? Or technically, yeah, no, we could use cis and trans since we have 2 equivalent groups. Well, actually, hold up. Because the groups I'm referring to are this ones. So we have the methyl group here and this carbonyl here, right? So those are trans to each other, right? And here they're on the same side, right? So this is just kind of a trend for NMR coupling is what's it called? For alkenes, right? Usually you have a for trans alkenes, right? The coupling constant's a little bit bigger, right? And generally you'll see like the trans stereoisomers are usually more downfield, right? And then cis are more upfield. right? Because if they're closer to each other, there's gonna be more shielding, right? But I don't think you would lose points if you drew it top or bottom, or maybe one or two at max, right? I don't know if that was the cis trans stuff in alkenes. I don't know if you were taught that in either one of Bisco's or Boson's class, right? But if you got one of these two structures, you'd probably get majority of the points for this question, right? Then knowing whether the alkene itself is cis or trans, right? That's just additional knowledge in terms of, NMR trends and stuff that you should just remember, right? But if you figured out most of the rest of it, it's pretty fine. But obviously with an IR, I mean, like I said, the IR, it would only help you a little. All it would tell you that is really you have the ester, not a carboxylic acid, right? But generally a 1H, a proton NMR spectra is enough to, figure out these questions. Okay, next question is going to be a little hard, but it just requires a little bit of thinking. And it explains it pretty well too. And so I'm gonna post parts of this. This is our, maybe let's go a little bit more down so we have space. So this is a little bit different deals all than you've seen. So I'll give everyone a few minutes to try that. There's a second part here I'm pasting as well. Okay, right. So there's a reaction known as the inverse demand Diels-Alder reaction, right? So I think I mentioned this before, right? I don't know if you directly learned it or whatever, but the principles are still the same, right? It's just kind of requires a little bit of thinking. So basically the main difference is diene is electron poor, right? Which we can see with electron withdrawing groups, and the dienophile is electron rich. So the first part is pretty simple. All you have to do is draw your MO diagrams, right? And indicate HOMO and LUBO. Second part is showing the transition state, right? And like I said, it gives you a lot of what, for this question, right? In the transition state is the HOMO of the dienophile and the LUMO of the diene that interacts, right? So, kind of laid out most of it for you, but shouldn't be too bad. So take a few minutes to try that. And there's only one more question left, which is related to peptides. It's not a peptide synthesis. Okay, let's do it. So for A, right, it's pretty straightforward. It's just MO diagrams, right? We have 1, 2, 3, 4 pi orbitals, which means we have 4 molecular orbitals, right? So we should have 4 levels, right? Let's start with the bottom one. Don't know why I'm in red still. Hopefully that's enough space. Okay, so let's start with the bottom one, right? Everything is in phase with each other. Also draw this one wave, kind of depicting that, right? Now, next one, we're going up a level. Therefore, we have 1 node, 2 nodes, 3 nodes, right? So 2 are in phase, 2 are out of phase, which creates a node in between them, right? You could think of this wave like this, right? Now we are trying to create 2 nodes, right? So you could have, what is it? Here, right? And then we can create a node here, keep these in phase, and then create our second node between this, right? And then the last one, they're all just out of phase, right? So if we see here, right, we get 3 nodes. And then in the last one, we just have 4 nodes, all out of phase with each other, right? This is a 4 electron system. Let me just redraw the structure here since I don't want to scroll up. N and Cn, right? 4 electrons, lowest to highest, right? So this would be Phi1, Phi2, Phi3, and 4, right? The one with the highest occupied molecular orbital, right? So highest energy level with the electrons in it. So this is our HOMO. And our lowest unoccupied one is the one right above, right? Pretty straightforward there. And now the second part is the diene itself, which is this, right? Oh, oops. This one's pretty simple. They're just either in phase or out of phase since there's only 2 molecular orbitals. Only 2 pi electrons, right? So this is our HOMO. And this is our LUMO, right? We're not at that part yet. So next part, right? It says reaction is an inverse of a Diels-Alder. In its transition state, we use the HOMO of the dienophile and the LUMO of the diene, right? So like I said, maybe I shouldn't have included that to make you guys think about it, but it's kind of question really lays out what you have to do here. So as long as you got these right, all you have to understand is from the first one, right? Because here, right, our dienophile, our typical dienophile, right, it's electron poor because of these nitrile groups, right? So we're going to use its LUMO, right? And then for our diene, which has a OR group, right? The ether group or whatever you want to call it, or alkoxy group, that's donating electron density in. So we're going to be using the HOMO here, right? And now we could just kind of line these up. So let's do this. All the orbitals. So here we have at the edges, that. And then the other one, right, is just your diene. Me here, right? And you could like this. Now remember, right, we're in 3D space. you could just flip it to the other side, right? So that way the orbitals line up. Essentially, we could draw it like this too. Be perfectly okay. It would just be the other face, right? Or this is on the bottom like this. And then all you have to show is interaction here, right? And that's it, right? And then since your dienophile is symmetric here, right? So, and see, and didn't ask for a product, but your product. Me. In terms of wedge or dash, it would probably be on a dash. It wouldn't really matter too much, but I would say it would just be on a dash because it would be below and it'd be closer to this carbonyl here because of the transition state. I'm not, because that thing is with the inverse demand, maybe because now this is electron poor, maybe that might be on the thing. So I'm gonna leave it this and I will just leave it like that. No stereochemistry indicated. Let's make a star here, right? But they didn't ask you for the final product. The main thing is, I don't know if, he'll probably just give you a more classic one, right? But, this is a good practice of the diagrams, right? In the transition state, right? Just make sure key thing is the orbitals line up the same phase, right? I didn't flip the HOMO. I flipped the entire molecule's face, right? Just so these could line up. If I wanted to, I could have also just, left it originally like this, right? And, have it approach from the top side or whatever, right? This is thermally loud. We didn't change any phase. We didn't change or excite any electrons. I literally just rotated this in space, right? That's what I did. I made sure to go over this when we did Diels-Alder for the first time, right? You're allowed to fully flip the molecules so the phases line up, right? This being on the top or bottom they're still both in phase with each other, right? These are just, you're viewing them, right? This is your eye, right? You're viewing them from different faces. This is from the top. You could say now you're viewing it from the bottom, right? The main thing is you're allowed to fully flip it, right? To match it up, right? You are not allowed to change actual phases. I didn't change any of the phases here, right? They're still both in phase with each other. If I did something like this, right? Then I excited it and did something else, right? Which is not what I did. Okay, so let's do the last question. Which is a pretty good one too. I don't know if Bisco would ask this, but this is kind of up his alley of questions he asks. I like this question. It has to do with bond rotation. Okay. Heck. All right. Peptoids are analogs of peptides, wherein the side chain R group is not on a carbon, but on the nitrogen instead, right? So typically amino acids that are, I guess, alkylated on the nitrogen, right? That's the main difference between the peptoid, right? And the peptide here, right? Essentially you have this, right? Peptoids have been studied for decades for their biomedical applications. Consider the structures of these biosynthetic molecules. Do you expect peptoids to have more or less C-N bond rotation as compared to peptides, right? So essentially it's asking you about the rotation of this C-N bond here. So take a few minutes, think about it. Maybe draw some resonance structures, right? That might help. And yeah, we'll talk about it. Exam 1, 2, or 3 is going to be on everything. I can't really answer that question because it's literally when he's making the exam, he's just going to go through stuff and pick it. I mean, I will tell you there's going to be one NMR question. It will probably be a deals holder question. Then one of the acidic questions can come out of any chapter, right? Then you just have to know trends or whatever. Maybe an aromatic question, right? And then, question 3 is just going to be literally from all the chapters you learned, right? Like we just did earlier, right? It could be any reaction from any chapter. And the mechanism, it's usually acid catalyzed mechanism, right? That's generally, even if it's a Lewis acid, right? I think on your first exam or maybe the second exam, you guys had that one with the, the acylation or whatever. But it's nothing, it wasn't too hard, right? It's just understanding that, you're going to use that as a Lewis acid. It's going to kick in, attack, kick out, all that stuff. But yeah, really, like he said in his email, everything is fair game, right? But generally, I've always seen one NMR question, usually one deals older, acid catalyzed mechanisms, and then some sort of comparison question, whether it's aromatic or acidity, right? And then you probably have 1 or 2 synthesis questions. I don't know. He said it's going to be a little longer. And remember, he said you guys can start at 7, which I have to figure out what time I'm going to get there. Damn, that is early. I mean, good for you guys because, you have more time, but like, I gotta leave my home early. Yeah, it's just unfortunate because, everything is booked in Marshak. So, at least you do have like what, 3 hours to do the exam, which is a lot of time, right? I don't know for Boson when his exam starts. I think it starts at like 2 or 3 in the same day, but I don't know what his time limits are going to be. I have no clue. I don't know what he would do for a thing. That's something that's up to him. Because I don't think he's done online exam. Oh no, he's done online exams for like his grad school classes, but those are much, much more difficult than this. I honestly don't know what he'd do for online. What I know Professor Andia did was he would just make an open book and just make the questions a lot more difficult, which a lot of people still struggled with. I don't know what Professor Bisco do. I don't think he's a fan of open book learning, and that's everyone has a different. I don't mind that because that it's hard to retain knowledge when you test it completely on open book. But circumstances are bad. Not everyone. All that stuff. I think he most like unless he says something, I'm pretty sure it's just going to be in person how you guys expect it. And that's for both. I know Boson sent the email out too, but it's most likely going to be in person because it's a pretty big room. A lot of people already dropped this class, right? He'll probably just spread you guys out even more, right? Wear a mask, wear an N95. Hopefully everyone's boosted and vaccinated, right? Yeah, I don't know. Unless circumstances changes over the next 3 days with Omicron or whatever. It's just probably going to be in-person normal exam. Okay, let's just finish up this question then, and then we are done, right? So really the best way to kind of look at this, right, is in terms of rotation, right? Obviously, it's hard to tell when it's in a single bond form, right? So what we could do is draw a resonance form where they're both sorry, it should be pi donation the other way. So this is gonna hear this, right? And then same thing here. So now if we draw this first structure, O minus NH and pH carboxylic acid. Okay, let's maybe move that over to the side a little. And the next structure here, right? Same thing, double bond this, right? And now you have your chain here. This is kind of similar to that question with aromaticity, where why does this have, it's hard for the, or the cis trans isomerization and stuff like that, right? It's kind of similar. Right, and the resonance structures will help explain that, because now if you look, right, so we know this bond has single bond character, but it also has double bond character, right? So we know it can rotate, right, but it's not going to rotate freely, and that goes for both of them because nitrogen's a very good pi donor, right? So when you look at the resonance structure, the key difference here, right, is this NH versus NPH, right? We know essentially, in like kind of, we drew this in 3D space, right? And this was the N, right? And we had some giant R group here, right? Remember, this is p orbitals and your sigma orbitals, right? And even though this switches between kind of, remember, there's nothing is set in stone, right? So it's still slightly like rotating, right? It's going to be a lot harder for this to rotate when you have a gigantic R group, or in this case, your phenyl group, benzylic group, whatever you want to call it, this gigantic R group with the benzene ring, right? As compared to something with the hydrogen, right? Essentially, there is much less rotation here because this R group is going to cause steric hindrance, right? So you could say that. You could also mention that technically, I guess this is 1, 2, 3. So this is tri-substituted. This is tetra-substituted, right? It's a lot more harder for tetra-substituted things to rotate. There's a lot more steric hindrance. The main thing is identifying that when you draw the resonance form, that there's going to be a lot of steric interference, steric hindrance here that prevents this bond from rotating, right, in its single bond form. And that's why the peptide has more CN bond rotation, right? Because it's a lot less sterically hindered, which allows it to rotate that bond a lot more easily compared to when it has some sort of alkyl group here. Right? So yeah, that's it. I will close this recording. It